say it's great to welcome all of you here again, like we said yesterday, to have be able to see all of you in person. It's really a pleasure. And I am really happy to be able to introduce our speaker this morning, Pavel Galashin, who will be talking to us about Pository varieties.
All right, thanks. Can you hear me? Yeah, all right, cool. Yeah, thanks a lot for the invitation. Yeah, thanks to the organizers for finally making this happen. And yeah, special thanks for removing all the black stuff from the screen. Yeah, so I'm going to talk about Positroid varieties, which the title is very vague and the abstract was very vague. But actually, I'm really going to talk about these objects. Can you see the pointer? All right, cool. So yeah, and this is joint work with Knutson Lam from Michigan. And before I talk about any of these objects, let me just give you a general outline of what I'm going to be trying to do, which is I'm going to be choosing, first of all, I'm going to choose a variety. So it's just a subset. For me, it's just going to be a subset of the k-dimensional space where some polynomials are 0 and some others are non-zero. And I'm going to assume that the polynomials have integer coefficients because then this variety is defined over any field. And I'm going to choose different fields. So one field I can choose is the finite field with q elements. And then this space becomes just a finite set. So its cardinality, the point count over fq is kind of one nice invariant you can compute for your given variety. And I'm actually going to be, yeah, let me draw this commutative diagram on the blackboard. So on the left, you have point count over fq. And yeah, so that's one thing you can compute. And another field you can choose is the field of complex numbers, right? If you choose complex numbers, then your space becomes some kind of, your variety becomes a nice topological space, maybe singular. And so you can study the beta numbers, right? The dimensions of the homology, and you can package them into the Poincare polynomial. And notice how for technical reasons, I'm using half integer powers of t. Right? So half integer powers correspond to odd cohomology and integer powers correspond to even cohomology. So let me write it down here. Poincare polynomial of your variety over C, which has a square root of t inside. And so that's basically it, right? So you get these two nice invariants which don't really talk to each other. Like in general, there should be no relation between these two objects. And so you get a commutative diagram with no arrows. And yeah, so actually, so not yet. The actual other thing I want to compute is something that sits on top of those and has a complicated name. So the mixed Hodge polynomial is just a polynomial, so the Poincare polynomial has a square root of t, but this one has a square root of t and a square root of q. And other than that, it's just a polynomial with positive integer coefficients. And yeah, so step 4 for me is going to be to compute this polynomial. And it has a pretty complicated definition coming from algebraic geometry. But one cool thing about it is that it's canonically assigned to your variety. So it has cohomology, which is canonically assigned, but actually there is secretly a second grading on the cohomology, which gives you more information. So yeah, and I'm not going to define. And another cool thing about this polynomial is that it specializes to both of those at the same time. So let me write it down. Mixed Hodge polynomial p of x has square roots of q and square roots of t. And it specializes to both of these. So if you send square root of q to 1, you get the Poincare polynomial. But if you send the square root of t to be -1 over the square root of q, then you get the point count up to some monomial in q. So the point count is an actual honest polynomial in q. That's what's going to happen. So yeah, and finally, I want to complete my commutative diagram. So I want to somehow find something that's below both of these. And let me try to do it like this. So I'm going to try to plug in everything q and square root of t to be equal to 1. And my arrows are dashed because the diagram doesn't actually commute. So q goes to 1 and square root of t goes to 1. And hopefully this thing in the bottom is an interesting number. So yeah, in general, you can always plug in q equals to 1 here and square root of t equals 1 here, but you would get different numbers. But when does this diagram commute? It commutes whenever the mixed Hodge polynomial has only integer powers of q and t. Yeah? Yeah, that's a good question. I could plug in -1, but actually, let me think about it. I don't remember what happens if you plug in -1, but I don't think you get an interesting number at the end. But here, of course, yeah, so interesting things happen when the diagram commutes. So when the polynomial has only integer powers, so that there's no half integer powers, and that means that it's equivalent to saying that the odd cohomology of your space vanishes. So there's only even cohomology. So in this case, if we're lucky enough, yeah, then we can study this interesting number combinatorially. And yeah, so this is a very nice story. And my first open problem for you is like choose your favorite variety and compute all those things. But of course, yeah, which variety? I mean, you can choose your own, but I'm gonna choose some varieties later, and you may have a guess which varieties I'm gonna choose. But for now, let me start with a warm-up example of the Grassmannian. So it's a very classical case. The Grassmannian is just the set of all linear k-dimensional subspaces of f to the n, right? So all k-planes through the origin. And then you can study this. It has a structure of a variety, which I'm going to explain later. But for now, yeah, you can choose your field to be the finite field of k elements and ask how many points, or you can choose your field to be the complex numbers and ask what is the Poincare polynomial. And it turns out that these two questions have the same answer. So to tell you the answer, let me introduce some notation. First of all, the q integer is just 1 plus q all the way up to q n minus 1. And the q factorial is here. So as you send q to 1, this becomes just n, etc. And finally, the q binomial coefficient is, by definition, you take the binomial formula and you replace every integer by the corresponding q integer. So it's going to be divisible, and the ratio is going to be a nice polynomial in q with positive integer coefficients. Right? It has a combinatorial interpretation as the sum over Young diagrams that fit inside a k by n minus k rectangle of q to the number of boxes of your Young diagram. So you get this nice polynomial in q, and then the claim is that the point count is literally given by this polynomial, by this q binomial coefficient, and then the Poincare polynomial with these half integer powers of t also turns out to be equal to the t binomial coefficients. And you may wonder, why are these two answers the same on the nose, and why would this even be true? And there is a simple reason, right? So there is something called the Schubert decomposition of the Grassmannian, which kind of easily explains both of these computations. But I'm not going to explain that because for me, the Schubert decomposition is not going to be important. Later, I'm going to consider different varieties where there's no hope even for something like a Schubert decomposition. So yeah, let me actually mention another reason, which comes from computing the mixed Hodge polynomial at the top. So it turns out that if you compute the mixed Hodge polynomial, it just contains no new information. So it has yeah, go ahead. Yeah, so you have, if it has a decomposition into affine pieces, yeah, which form a CW complex, then yes, so the Schubert decomposition subdivides your space into even dimensional cells, each of which as a field is isomorphic to like a power of c. Okay. Any other questions? All right. Yeah. So the cool reason, I guess, is that yeah, this mixed Hodge polynomial has no new information. So the thing you get at the top is still just Q binomial coefficient, and therefore, in particular, none of these polynomials involve fractional powers of Q and T, and therefore, you get an interesting number, which in this case is just the binomial coefficient. Which, of course, it's an interesting number, but you know which number is more interesting than binomial coefficients? The Catalan numbers. So of course, yeah. And let me define Catalan numbers for you. And I'm gonna, of course, you all know, but let me define something slightly more general. So these rational Catalan numbers are defined. You choose two integers k and n, which are coprime. And then the Catalan number is just the ratio of a binomial coefficient divided by n. And it's going to be divisible. So the ratio is going to be an integer, which has a combinatorial interpretation. So it counts the number of dig paths inside a k by n minus k rectangle. To give you an example, here's the case of a 3 by 5 rectangle. So you have these seven dig paths. And as you can check, that if you plug in n and k here, you're going to get 7. So that's going to be hopefully something at the bottom vertex of my commutative diagram. That's my hopefully interesting number. Now, how do you define Q analogs of this number? One way to do this is to look at this formula and replace every integer by the corresponding Q integer. Then it's still going to be divisible, and the ratio is going to be a polynomial in Q with positive integer coefficients, which in this particular example looks like this. So it's a sum of 7 terms. If you send Q to 1, you get 7, and it all works out very nicely. Now, there is another Q analog, which, so remember, for binomial coefficients, we had some sum over Young diagrams inside a k by n minus k rectangle. And here you can do the same. You can take the sum over dig paths of t to the area of your dig path. And by area, I'm just going to mean, so here's the example. The area is the number of boxes strictly between my dig path and the diagonal. So you get the power of t to the number of these red boxes. And you can see that these two polynomials are not the same, right? The top one has coefficients equal to 2, and then the bottom one doesn't. So yeah, and that's where the complexity of this picture actually shows up for the first time. So because these two things are different, there should be something interesting at the top. And this something interesting is, of course, as you know from yesterday's talk by Eugene, is that it's just the QT, the rational QT Catalan number, which is defined combinatorially. So it's a sum over dig paths. So it's the same sum as here. So t to the area as before, but now I stick a power of q into every one of these monomials. So what I'm going to see is something like this. It's q to the dinf, where dinf is the number of diagonal inversions of your dig path. And yeah, so Eugene explained yesterday what are these diagonal inversions. The usual inversion is just a horizontal path followed by a vertical, that's to the left of the vertical path, horizontal step to the left of a vertical step. And then they form a diagonal inversion if there is a line parallel to the diagonal, which crosses both of these at the same time. So you get some polynomial in Q and T, which surprisingly enough is symmetric. If you swap Q and T, you get the same answer. This is a super hard problem to prove this combinatorially. But yeah, you get this commutative diagram. So the question is, what is the geometric interpretation of that commutative diagram? And let me try to give you the answer. So going back to the Grassmannian, one definition is k-dimensional planes in the n-dimensional space. Another more convenient definition is if you choose a basis of this k-dimensional space, you're going to get k rows, you're going to get a full rank k by n matrix whose rows form a basis. And if you choose a different basis, then the two matrices are related by row operations. So by invertible row operations, so that's the other definition that you get. And this one is more convenient because we have natural coordinates on the Grassmannian, namely, I can look at maximal minors of my matrix, maximal minors of my matrix. So yeah, you choose any k columns, and then you take the corresponding k by k determinant, and you look at all such and choose k different determinants. Yeah, so using these coordinates, let me define what Thomas and I call the Catalan variety. Is by definition, it's the subset of the Grassmannian where all maximal cyclically consecutive maximal minors are all equal to 1. So, and here I'm assuming that the GCD of k and n is equal to 1. So yeah, delta 1 up to k is equal to 1, delta 2 up to k plus 1. And so at some point it starts wrapping around. So the last minor is delta n, 1, 2, up to k minus 1. And I view these values as a set, so I can sort them. There is no signs involved. So I get this variety. For example, for the case where k is 2 and n is 5, I'm looking at 2 by 5 matrices. And then I know that the first k columns form a non-zero determinant, so I can apply my row operations uniquely to force them into the identity matrix. And then the rest of the entries are just going to be some arbitrary entries, but they have to satisfy these extra equations. Right, so for example, this determinant is negative a, so negative a has to be equal to 1, and then ae minus bd has to be equal to 1, bf minus ce has to be equal to 1, and finally it wraps around. So there's one more minor on columns 1 and 5, which is equal to f. So f also has to be equal to 1. And so that's it. You get 6 variables, 4 equations. That's your Catalan variety. And it's a nice exercise to compute the point count. And if you're brave, the Poincare polynomial of this thing over C. But in general, yeah, what is this whole diamond for this particular variety? And let me give you the answer. So the answer is a theorem that Thomas and I proved some time ago. It's that all the answers for this Catalan variety, whoa, no way. Okay, enable. Nah. Okay. Okay, when I'm talking, it's gonna appear. Let me try to move this. Nice. Okay. Perfect. Yeah. So it's still there. Okay. Whatever. So the main result, the first main result of this talk is this. Now the pointer doesn't work. The main result of this talk is this theorem here. So you already know what the main result is going to be. So the whole commutative diagram, or the mixed Hodge polynomial, is the rational QT Catalan number, and then the point count is given by one Q analog, and the Poincare polynomial is given by the other Q analog, and finally there is no half integer powers of Q and T, so the interesting number is just the rational Catalan number. So yeah, go ahead.
If you have a point in the open Pository, right? You always use the Taurus action to make sure your presence is equal.
Yes, when the GCD is 1, I'm gonna say it on the next slide. Yeah, thanks. Okay, the question was whether I can use the Taurus action to put things from the open Pository to Catalan variety. The answer is yes. Okay, so this is the first main result, and by the way, it answers one of the open, modulo some computation. There was an open problem in Sergey's talk yesterday about grid quivers not being mutation equivalent to each other, and yeah, this basically reduces the problem to showing that at least when the GCD is 1, that the QT Catalan numbers for different, yeah. I can't hear you, sorry. Okay. Am I actually using the complex structure to compute the mixed Hodge polynomial? Well, I'm using this structure of an algebraic variety. Yeah, so it's yeah. This is not an easy computation. This is right. Yeah, yeah. We're using a lot of sheaves and etc. for this. So Yeah, okay. Any other questions, by the way? Yeah?
Is this a affine variety or projective variety?
This is an affine variety. So, I mean, 6 variables for equations, and in general, it's always going to be, this Catalan variety is an affine variety. I mean, quasi-affine, but yeah. Okay, any other questions? All right, yeah, so the grid quivers are not mutation equivalent because the corresponding rational QT Catalan numbers are different. And now let me try to discuss some consequences of this theorem. First of all, going back to this example here, the point count turns out to be equal to q squared plus 1. And the Poincare polynomial is just given 1 plus t. So there is no square root of t here, right? It's kind of skipped. And the rational QT Catalan number is just q plus t. So rational Catalan numbers include the usual Catalan numbers as a special case, right? When k and n minus k differ by 1, then these are just usual Catalan numbers. So 2 is a Catalan number, as everybody knows. So that's the case corresponding to that Catalan number. Now, okay, let me discuss some consequences. And the first one I'm going to discuss is, well, how do you relate this? Of course, we didn't invent this variety. It's very closely related to open Positroid varieties. So here's the definition of one of, I'm only going to consider open Positroid varieties. So here's the special one. It's the unique top dimensional open Positroid variety. And this is just given by the subset of the Grassmannian. It's an open dense subset where the cyclically consecutive maximal minors are just all non-zero. And this is defined for any k and n, not necessarily coprime. And so what is this? What is the relation? I'm taking the same minors, but on the top, I'm setting them all to 1. On the bottom, I'm asking that they're all non-zero. The relation is the so-called Taurus action, right? Where by torus, I mean an algebraic torus, which is just the set of diagonal matrices with determinant 1. And these diagonal matrices, they act on the Grassmannian, and they preserve, like, Grassmannian is k by n matrices, so you rescale the columns of your matrix. And then they preserve this open Positroid variety. And so one cool fact is that this Taurus action is free, right? Meaning that non-trivial elements act without fixed points. So the action is free if and only if the GCD is 1. And in this case, you have this nice relationship between the two varieties. So essentially, once you strip off enough of these C star factors, you get the Catalan variety. And it's a cool exercise for you to, like, if the GCD of k and n is 1, show that you can actually, given any matrix satisfying these conditions, all these minors are non-zero, show that you can find a unique diagonal matrix which rescales all the minors they all become equal to 1. Okay, now using this lemma, right? So if we have computed the whole commutative diagram for the Catalan variety, it's now easy to do this for the top open Positroid variety. So first of all, the Poincare, the mixed Hodge polynomial, differs by the simple factor of q squared of q plus square root of t to the n minus 1. And then by kind of these specializations, the point count has a power of q minus 1, and then the Poincare polynomial has a power of 1 plus, yeah, I'm not going to move this thing away. It's 1 plus square root of t to the n minus 1 times the previous Poincare polynomial. Okay, so in particular, yeah, and by the way, there is half integer powers of q and t, and that's why my commutative diagram no longer works. So for Pository variety, if you plug in k equals to 1, you get 0. And okay, now this is all good, and let me try to mention a curious corollary of this approach. So I'm going to compress all these things on the top to a few lines. So Catalan variety here is here, and the open Pository variety is here. And this is how they are related when the GCD is 1. Then I already told you how to compute the point count of the Catalan variety. Right? The point count of the Catalan variety is just this Q analog of the rational Catalan number. And then I also told you what is the point count of the Grassmannian. That's the Q binomial coefficient. And now, since we have this simple factor, I also told you how to compute the point count of the open Positroid variety. So if you combine all these things together and divide one by the other, you get this kind of interesting probabilistic interpretation, which tells you that, so assume that the GCD is 1, otherwise this is false. So you take the Grassmannian of k planes inside fq to the n. That's a finite set. So pick a uniformly random point of that set. So uniformly random k plane inside fq to the n. Then the probability that all of its maximal cyclically consecutive minors are non-zero, the probability that belongs to the top open Pository variety is just given by this simple formula. Q minus 1 to the n over q to the n minus 1. And yeah, so this probability is less than 1 as expected. But the weird thing about it is that it does not depend on k. So the whole statement depends on k because k has to be coprime on n, with n. But other than that, it doesn't depend on k, which is super weird. The Grassmannian depends on k and the open Pository variety depends on k, but the answer does not. And yeah, so Thomas and I have no explanation for this. And we have a proof, but we don't have an explanation. And so one open problem is to prove this result directly without, yeah. So we use knot theory for that, but so you can only prove the non-dependence on k, because when k is equal to 1, then this ratio is, of course, is very easy to compute that it's correct. So yeah, that's my first open problem to you. Please solve this. And let me know if there's any, but yeah. Yeah, it's going to be a different probability when k is not coprime to n. Yeah, I think it does. I mean, it at least depends on the GCD, but I have to think about it. Yeah, go ahead. Yeah, this sounds kind of like the cycle lemma, but even for q equals to 1, I mean, for q equals to 1, this ratio is 0. But yeah, I agree. It sounds similar with the cyclically consecutive minors being non-zero. And we thought about how to make this precise. But yeah, there's, I don't want to go into it. But yeah, this is an honest, if you come up with some cycle lemma approach to this, it's going to be amazing. Yeah. Any other questions? Okay. Now, since the talk is about Pository varieties, let me try to at least define arbitrary Pository varieties. And you don't really have to listen to this definition, but let me still mention it because it's important. So again, here's the definition of the Grassmannian. And then the Grassmannian is subdivided into these pieces called open Pository varieties. So these nice smooth pieces, which together form as disjoint union, the whole Grassmannian. And then to define these pieces, let me take one of these k by n matrices and let me associate to this matrix a certain map. So first of all, I'm going to look at the columns of my matrix, M1 up to Mn, and then I'm going to label them. I'm going to continue this labeling cyclically. So the Mn plus 1 is equal to M1 and etc. So it's just cycles around these n columns. And then my map associated to a matrix, so f sub m is a map from 1 up to n to 1 up to n, is just the minimum over all j bigger than I of such that mi belongs to the span of mi plus 1 up to nj. In other words, you take the ith column and then you scan to the right of it until you find until it belongs to the span of a bunch of columns to the right of it. And then j is the minimal index such that this is true. And then you take j, so j could be bigger than n, and then you take it modulo n. So you get a map from 1 up to n to 1 up to n. Associated to every one of your matrix, and it's invariant under row operations. And also another cool fact is that this map is a permutation. This is non-trivial to see, but for every full rank matrix, you do get an honest permutation. And so modulo some details about fixed points of permutations, which the experts know and the rest of you shouldn't care about. The open Pository variety is just the set of row spans of all matrices whose associated permutation is equal to f. So these my pieces are defined according to these different permutations for different matrices. And for example, the top dimensional Pository variety, which I told you about previously, appears as a special case when, so you choose a particular permutation which sends I to I plus k modulo n. then it's pretty easy to see from this definition that the corresponding condition on the minors of my matrix is that the maximal cyclically consecutive minors have to all be non-zero. That's an if and only if. So, but in general, you give me a permutation and I give you a variety. So what is the point count, the Poincare polynomial, what is this whole commutative diagram for a given permutation? That's my question. And to answer that question, it turns out I have to talk about knots and links. So let me, first of all, remember that a knot is just you take a piece of rope, tangled together into three-dimensional space. So an embedding of a circle into three-dimensional space. And a link can have several components. Right? It's like a knot, but you have several circles tangled together in some way. So let me define for you Positoroid links to every permutation, right? So I have this Positoroid certification into permutations, and to every permutation, I'm gonna associate a link. So I'm gonna associate a link in the three-dimensional space, but for me, it's gonna be convenient to draw this link on the torus. Right? Because the torus embeds into three-dimensional space. So I'm just going to draw a link diagram on the torus. And here's a completely random permutation without fixed points. Let me try to draw the diagram. So 1 goes to 5 means that I draw an arrow from 1 to 5. So all my arrows point in the northeast direction. 1 goes to 5 and 2 goes to 4. And notice how these arrows cross each other, so I have to draw an overcrossing there. So the rule is that an arrow which has a higher slope has to be drawn above the arrow with lower slope. So here, the red arrow is above the blue arrow because it's more vertical. So yeah, 2 goes to 4, and then 3 goes to 6, and 4 goes to 3. This is a very vertical arrow. 5 goes to 1, and 6 goes to 2. Oops. So yeah, so that's my. And then to convert this into an actual link diagram on the torus, I just kind of ignore all these numbers. And this is a drawing of a link with 2 components. So the colors represent components, and they also correspond to the cycles of my permutation. Yeah, I get a link. That's the Positroid link. And yeah, so this construction is kind of new. It doesn't, it's going to appear in our paper with Thomas, but there are many different constructions for the Positroid links, which appear in all these different papers. And they're all equivalent to each other. So yeah, the bottom line is that you can now just forget all these definitions. You give me a permutation, and I'm going to give you a Positroid variety and a link associated to your permutation. And the question is, how is the link related to the open Positroid variety? And what's the connection? And let me try to, the connection goes through link invariance. Right? So if you have 2 links, you want to distinguish them. Like, can one be transformed into another without passing the rope through itself? And for that, it's useful to compute different knot invariants. And the one I'm going to be interested in is the Homfley polynomial. So it's defined, it's a polynomial, it's a Laurent polynomial, which depends on the link in 2 variables. So when the link is the trivial knot, then the polynomial is 1. And then if you have 3 different links, L plus, L minus, and L0, which satisfy this skein relation, so the 3 links should differ as follows. They imagine 3 giant links which only differ around a single crossing. So L plus is an overcrossing, L minus is an undercrossing, and L0 is you resolve the crossing. And then yeah, the 3 polynomials, the Homfley polynomials, are going to be related by this expression here. And it's not trivial to show that this actually defines the link invariant, but it is true. Yeah, and one result that kind of started this whole project was we noticed with Thomas that the point count of any open Positroid variety up to a factor of q minus 1 is just on the nose equal to the top A-degree coefficient of the Homfley polynomial of the corresponding link. So yeah, that's the easy way to compute the point count because the Homfley polynomial can be, it's already in Sage. And okay, now you can, so at least the point count for arbitrary links, for arbitrary permutations, we know from this theorem. And now, first of all, this q minus 1 factor again appears from the Taurus action. So for the top open Positroid variety, this was if and only if the GCD is 1. But for an arbitrary permutation, the torus acts freely if and only if f is a single cycle. if and only if the corresponding link is a knot, meaning that it has only one connected component. And in that case, we can upgrade this theorem using Havanov-Rosansky homology that Eugene talked about yesterday. So yeah, it has a complicated definition. You have to do some work with Zorgel bimodules, and the trade-off is that you get an extra variable. There is a t variable here that's not present in the Humphrey polynomial. And you can get the Humphrey polynomial by a suitable specialization. And so the actual result that we proved is that at least for when your permutation is a single cycle, the corresponding mixed Hodge polynomial is the top 8 degree coefficient of the Havanov-Rosansky homology polynomial. Yeah. And if you're interested in something that's not a single cycle, then the answer, you can no longer take the free torus quotient, but you replace the left-hand side with the torus equivariant cohomology with compact support, and it all works out. So yeah, that's the theorem. And yeah, so before I mean, this is a result which I have to tell you, but this is not a conference on proven results in algebraic combinatorics. So let me try to use this result to show you like where it kind of opens a whole field of open problems. So I'm going to try to, yeah. Okay, go ahead.
So both sides, is there a categorification?
Is there a categorification of what?
Instead of saying this number equals this number,
Yeah, we can. There is what we actually prove is some, some isomorphism between the cohomologies of sheaves and versus this Zorgel bimodules cohomology. Yeah. So, yeah.
This gives
Could you speak up?
well, this gives you a statistical permutations, right?
Well, yeah. For each permutation, you get a QT polynomial. Yeah, but we don't know what this. Yeah, I'm going to talk about the statistics a bit later. But yeah, in general, this gives you a mystery of like you give me a permutation, I give you a QT polynomial. What is the answer? Yeah. Any other questions? All right. So let me reformulate this theorem using my diamond here. So there it goes. So at the top, you have the Havanov-Rosansky homology. And then on the left, you have the Humphrey polynomial. On the right, the Poincare polynomial is equal to whatever. But what happens at the bottom, right? Is there an interesting number for any one of your permutations? And yes, or in other words, like, does this diagram commute whenever f is a single cycle? So is it true that this mixed Hodge polynomial doesn't have any half integer powers of q and t? And the answer turns out to be no. So, and unfortunately for us, there are some permutations. The smallest one we know is on 14 letters, so it's a huge example. And yeah, you get some, and in this example, there's like just a tiny monomial which has a half integer power, and the rest is integer. But yeah, still this is a counterexample. So the problem now becomes, can you find some nice class of permutations where you get interesting numbers? And if yes, what are these interesting numbers? So let me try to give you one nice class of these permutations. So here's a construction that we came up with Thomas. What you do is, and this is going to sound weird, but it actually naturally pops out of the Positroids approach. So you start with a concave curve from 0, 0 to n minus k comma k. Just choose any concave curve. And let's say it's generic. So it doesn't pass through any lattice points. And then, I don't know if you're going to see it, but I'm going to slightly move this curve up. So you can see that it moves up a little bit so that it doesn't pass through any lattice points, even 0, 0. And then I'm going to take this curve and I'm going to project it onto the torus. And this is going to look pretty cool. What you're going to do is you're going to scan the curve from left to right, and you're going to draw it on the torus like this. So let me go back, and yeah, so this tiny line segment on the left goes here, and then the next line segment goes here, and then the next one. Yeah, so you just project every unit square onto this, just draw them on top of each other. And at some point, your segments of the curve are going to start intersecting. So the rule is, again, a segment of higher slope is above a segment of lower slope. You keep drawing this segment, this segment, this segment, and eventually you arrive at the point where you started. And yeah, so that's a link drawn on a torus. And that link on the torus happens to be a link, it happens to be a Positroid link for some particular permutation, which you can read off from this picture. So you just put these numbers on the diagonal, and then your permutation sends 1 to 6. And yeah, so here's the permutation. It sends 1 to 6 and 1 to 6 and 2 to 1 to 6, 2 to 4, and etc. So this happens to be a Positroid link. And of course, the actual, if you wiggle your curve around a little bit, the permutation is going to change, but the link and the this diagram is not going to change. So so the actual answer, the link, which happens to be a knot, because this permutation is always a single cycle, it only depends on the kind of, it doesn't change as long as you don't pass your curve through any of the lattice points. So it depends only on this Young diagram that stays above the curve. And so we naturally have this family of commutative diagrams for Young diagrams which avoid a concave curve, or above a concave curve. So yeah, what is this diagram for those permutations? And so again, let's say you take a concave curve and take the corresponding permutation, then the only thing we were able to show so far is that, so we weren't able to compute the point count, right? The point count is, I mean, there are some formulas and recurrences. There's a lot of tools to compute the point count, but we weren't able to write it in some positive combinatorial expression for it. But if you send Q to 1, then the answer is the number of dig paths which stay above the concave curve. So that's one theorem we proved. And then conjecturally, we have a guess for the Poincare polynomial. That's just the sum of T to the area over the corresponding dig paths. And we even have a guess for the thing at the top, right? So the mixed Hodge polynomial, conjecturally, and we have a lot of data for that, is just the generalized QT Catalan number that Eugene mentioned yesterday. So remember, there was a gigantic summation over standard Yan tableau in his slides yesterday. So conjecturally, yeah, the mixed Hodge polynomial is given by those generalized QT Catalan numbers, but we don't know how to prove it. And so the open problems for you here are, first of all, I think like the problem that's most accessible is just to compute the point count. So find a statistic on Q which sort of explains this point count. And another more complicated problem, if you like guessing statistics, is you should find a statistic dinf. So when your curve is just a straight line, then dinf is diagonal inversions. But if you have a concave curve, then you should choose some other similar statistic which depends on the shape of the curve, and such that these generalized QT Catalan numbers, which you can easily compute in Sage, are given by the sum of T to the area times Q to the dinf. So yeah, that's an open problem, and I spent some time playing with it, but yeah, we couldn't figure out what should be a natural dinf statistic. Okay, and now let me try to mention a couple of generalizations in the remaining time. If you have any questions on this, let me know. Yeah, go ahead. Yeah, that permutation is not for such. Yeah, so we introduced some class of repetition-free permutations, and that one is not repetition-free. Any other questions? Yeah.
So if you don't bottom by the course, you look at the point count of the Pository variety, is that?
That's usually 0. Yeah, the point count of the Pository variety is usually divisible by Q minus 1 to some power. So, yeah, but you're talking about this polynomial or this specialization?
No, the other, yeah.
Yeah, this polynomial. Yeah, if you multiply it by Q minus 1, and yeah, it's still like there's going to be some power of Q minus 1 times this thing. So yeah.
So do I understand? If you just look at the point count of the Pository variety, is that a
Yeah, the point count of Positroid variety is an R, is Kazhdan-Lustig R polynomial, because Positroid varieties are projections of open Richardson varieties. Yeah, that gives you a recurrence to compute them. Yeah, so there are many recurrences to compute this number, but there is no positive one that we know of. Well, you can for general open. Yeah, actually, I'm going to mention them on the next slide. Let me tell you what I can do for open Richardsons. Any other questions on this? No. All right. So very briefly for the experts in the room, such as Steven, let me mention. Oh, actually, no. Where is? Okay, I guess I'm going to talk about open Richardsons a bit later. But for now, let me talk about cluster algebras, which is something I like to talk about. So as Sergey mentioned yesterday, you can start with a quiver, and then you can mutate, and you get a bunch of quivers, and then there is some commutative ring associated to that mutation class of quivers called the cluster algebra. So yeah, it's just some commutative ring, which I'm not going to define. But let me consider a special subclass of cluster algebras called locally acyclic cluster algebras. Because in general, cluster algebras are hard. Cluster algebras are hard, and locally acyclic cluster algebras are, I'm not going to say easy, but yeah, I mean, acyclic cluster algebras are easy, but locally acyclic is sort of medium well. Yeah. And so if this definition is recursive. If your quiver has no arrows, then by definition it's locally acyclic. If it has some arrows, maybe if it looks like this, so the game is to mutate your quiver until you find something called a separating edge. And I'm not going to give you a general definition of a separating edge, but the simplified definition is you mutate until you find a source vertex. So here I'm assuming there's no frozen variables, so these are all mutable vertices, and yeah, you mutate until you are lucky enough to find the source vertex, and then you choose one arrow from, well, let's say x to y from the source vertex x, and then you look at the three quivers which you can obtain by either removing x or removing y or removing both x and y. So you get these three smaller quivers, and then you recursively check whether each of those is locally acyclic. And if they are, then by definition, your quiver Q is locally acyclic. So this gives you some recursive way to work with these with the corresponding cluster algebras. And in particular, one theorem that we proved is that if you combine our paper with a paper by Miller and Speyer, what you see is that for any permutation, the open Positroid variety is a locally acyclic cluster variety. So in other words, what this means is that, so it's a variety, so it has a ring of polynomial functions in that variety, and that ring happens to be equal to the cluster algebra for some natural quiver that's associated to it. And moreover, that quiver is locally acyclic, and that part is due to Miller and Speyer. So why would you prove such a, by the way, this theorem also relies on some other works by these people. And why would you try to prove such a result? You know, it sounds like a useless commutative algebra exercise, but I mean, to me, it sounds pretty cool because this isomorphism, like this ring is defined in a very, very different way than this cluster algebra. So the fact that they are on the nose the same is kind of surprising. But let me try to, we had a particular application in mind for this result. So let me try to explain what we had in mind. First of all, here's the theorem again. There is a result by Lam and Speyer about these locally acyclic cluster varieties. Namely, if you have a locally acyclic cluster variety, then the mixed Hodge polynomial is Qt symmetric and Qt unimodal. Qt unimodal means that you fix the total degree of Q and T, and then the sequence of coefficients is going to be unimodal for each fixed degree. And in particular, if you combine these two theorems, you get this corollary that these open Positroid varieties, when F is a single cycle, their Taurus quotients as well, they are all locally acyclic cluster varieties. So in particular, their mixed Hodge polynomials are Qt symmetric and Qt unimodal. So just for free, you get this result, which, by the way, the proof of this theorem is very, very cluster. Right? So they actually use local acyclicity to do this recurrence and write down long exact sequences. And then the SL2 action comes from the GSV form, which is defined in terms of the quiver, and etc. But yeah, so you get this corollary, and in particular, remember, there's one special case when this polynomial is the rational Qt Catalan number. So you get kind of for free that rational Qt Catalan numbers are Qt symmetric and Qt unimodal. And so one application of this abstract linear algebra theorem, abstract commutative algebra theorem, is that you get these combinatorial consequences about combinatorially defined Qt Catalan numbers. And one of them is actually new. So this Qt unimodality for the rational Catalan numbers, Qt Catalan numbers, actually, at the time, it was a new result, which was kind of surprising. So yeah, and there were many works by different people related to these things. So the symmetry was shown by Mellet in the proof of rational shuffle conjecture, and etc. And yeah, but let me mention one kind of reformulation of the previous open problem. So here's another way to state the open problem. Let's say I give you a concave curve and you have your computer, then can you guess the statistic which depends on the concave curve such that this sum is Qt symmetric? That's it. Can you find a natural statistic, div-like statistic on dig paths which makes this sum Qt symmetric? And yeah, I tried that and couldn't do anything. So yeah, that's one open problem. And now, finally, let me briefly mention, actually, you know what, let me skip the Richardson varieties part, even though I promised to tell you about it. Let me actually, I'm just gonna skip the Richardson part. Okay, Richardson varieties are cluster varieties. That's, and then there's parallel work on that by these people, because I wanna tell you, yeah, this is some stuff for the experts, which they can later ask me about, but let me instead show you some pictures. So this is all very nice, but yeah, here are some pictures. So you can generalize this whole story for arbitrary Planar graphs. And what is a planar graph is just, Planar graph is just a planar graph with vertices colored in black and white in any way you want. And then, so it's drawn in the plane, there is no kind of boundary disk around it. And two things you can associate to a Planar graph are, first of all, a quiver. Right? As Sergey showed you yesterday, you take the planar dual and then you orient the arrow so that the white vertices are to the left and the black vertices are to the right of each arrow. So around each white and black vertex, you're going to get these oriented cycles. So that's one thing, and you ignore the outside face. And another thing associated to a Planar graph, instead of the quiver, you can also associate a link to a Planar graph. And this construction comes from these two papers. So these papers give you very nice, beautiful construction, but I'm going to give you an ugly version of that construction because I want to be concrete. I want you to go home and be able to draw pictures. So here's a, I mean, to make it concrete, you have to break the symmetry. So let me break the symmetry a little bit. The way you associate a link is as follows. First of all, you draw all strands. Right? These are known as zigzag paths. So a strand just turns left and right. So this orange strand, let's say, it turns left at white vertices and right and black vertices, left, right, and it circles around. So yeah, each one of these components is going to be a component of my link, and this I'm going to try to make it into a planar diagram of a link. So I need to tell you which of these crossings are over or under crossings. And the rule is that you look at any crossing. Let me look at, let's say, this crossing point here. So the blue strand points to the left, and the purple strand points up. Right. So you look at the complex arguments of the tangent vectors. So up means the argument is pi over 2. To the right means the left means argument is pi. Pi is bigger than pi over 2. So the blue strand is going to be drawn on top of the purple strand. That's it. I just compare the complex arguments. And I'm always going to assume that the arguments are between 0 and 2 pi. So that's what, between 0 and 2 pi is where I break the symmetry, right? If you rotate the picture, the sum over crossings are going to become under crossings. So far, this is not quite well defined, and it looks stupid. Like this green curve is not really linked with anyone. So there is this extra step, which is annoying, but you have to do it. This extra step is you have to mark all locations where the argument is 0. So that's where I break the symmetry, and these locations are marked with these little rectangles. And then at each one of these locations, you require that the strand has to travel to the boundary and back. So let me show it for the red strand. The red strand has to travel to the boundary above all other strands and come back below all other strands. That's the, and the reason it has to travel above is because if as you approach this point, the argument is very close to 2 pi. So 2 pi means above everybody else. So you go above it, and then here the argument is very close to 0. So you go back below everybody else. And you do this for all these other little rectangles. I didn't draw it, but yeah, this orange curve would have to go up below all other strands and come back above all other strands. So yeah, you get a link for any playback graph, and this construction is invariant under rotations, square moves, and everything. So it's just an, yeah. Yeah, this is a, yeah. You can think of this as a disk times a circle, where you, for the boundary, you identify the circle into the point, and it becomes a 3-dimensional. Yeah, this is a projection from a 3-dimensional sphere. Correct. Any other questions? Okay. So, anyways, the bottom line is that you start with a playback graph, and then you get a quiver and a link. How is the quiver related to the link? And let me mention one conjecture, which Thomas and I formulated. So for any playback graph, you can look at something called the cluster variety associated to the cluster algebra, and you can compute the number of points over FQ in that. I mean, it's a scheme in general, but you can compute the number of points over FQ, and the conjecture is that the result is going to be equal to the top 8-degree coefficient of the Humphrey polynomial of the associated link. So this is for reduced playback graph, if you know graphs, if you know what these are, this follows from our theorem with Thomas, but this can be formulated for any playback graph. And we are being slightly optimistic here because the actual data that we have is only for locally acyclic quivers, right? Because if the quiver is not locally acyclic, we don't have any tools for the point count, but if it is locally acyclic, then I basically have a sage program, which you don't really have to think about the spec or anything else. There's a sage program which you plug in the quiver and it mutates. And that quiver, if that quiver is locally acyclic, then the output is just the point count. So there's a very simple recurrence which comes from this locally acyclic definition, essentially. And that recurrence is super similar to the recurrence which defines the Humphrey polynomial. So, and in some cases, it's actually on the nose the same recurrence. So we were able to show for a class of graphs, which we call like leaf recurrent, when your source vertex has to be a leaf. We show that in that case, the conjecture is true. So an example is these playback fences, which are, you draw n strands, and then you put arbitrary black, white, black, and black, white bridges between in any way you want. And then the claim is that the conjecture holds. So the point count is a specialization of the Humphrey polynomial. But in general, there are other locally acyclic quivers where, coming from playback graphs, where we don't know how to show this. And one unfortunate thing that so we were originally hoping that any playback graph would give us a quiver that's locally acyclic, but the answer is no, because we found this example in Muller's paper. So this quiver is not locally acyclic. It comes from a 4-punctured sphere. And yeah, so the open problem for you is to find a class of playback graphs such that the quivers are locally acyclic and compute the whole commutative diagram. So the point count, the Poincare polynomial, and what is the interesting number for those playback graphs. And that's it. Thank you very much.
Thank you, Pavel, for the lovely talk. Are there questions?
What kind of knots do we get in this way? No, I have no idea. So for reduced playback graphs, we don't know if all knots we get are algebraic. So we don't have examples of non-algebraic knots. So it could be that all Positroid, like all actual Positroid links are algebraic. But for more general Richardson links, we know that they're not algebraic. Yeah, we don't really have any nice characterizations of those. Should I ask people or do? Okay, go ahead. Okay. Yeah. 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 Okay. It's the Bott-Samuelson thing. Okay. Good.
Repeat the question.
Oh yeah, the question was this the cluster algebra related to the Bott-Samuelson variety? And the answer is yes. Yeah, I can see who is asking the question, but how? Ah, okay. Yeah, well, at least if all the bridges are of the same color, then there is something called the Bott-Samuelson variety associated to a braid word, which is like an iterated P1 bundle or whatever. And for that variety, there is a cluster structure by Wang and Shan, which the corresponding quiver is the Playbig graph quiver for this Playbig graph. Yeah, go ahead.
Two questions related to the combination. So one is that so you see that so you have said that that whole thing depends on the contact, and that there will determine a permutation based on this. So it looks like is that
So the question was, I had these Young diagrams and permutations associated to them. So is there an easy combinatorial rule for associating that permutation to a Young diagram? And the answer is, first of all, there's many permutations. If you choose your curve to be slightly different, the permutation is going to change. But yeah, as far as easy combinatorial rules, that's the easiest one I know. Yeah, I don't know any easier way to get from. And on the torus, you would actually get different. So as knots in the thick torus, you would get different knots, but in the three-dimensional space, you will get the same links. So there are some, yeah. So good point. Yeah. So there were the question was in Eugen's talk there were these DIs which the generalized Catalan number depends on, and these DIs are so if you have a general Young diagram above a concave curve, if you have a Young diagram like this, then the DIs are D1, D2, and then D3 is going to be 0, D4. So these are just the length of these horizontal line segments at every. So the differences between the adjacent entries of your partition. That's the D's from Eugen's talk. Go ahead. To extend into what? To projective Richardsons. Yeah, okay. So we thought about this. Positoid varieties are special cases of open Richardson varieties. And where are they in my slides? That's the slide I skipped. Yeah, there you go. Yeah, so we thought about this a lot. And in particular, yeah, our result about KR homology generalizes to Richardson varieties. So this actually is the most general result we have. And yeah, we also thought about the cluster structure for open Richardsons, and we actually found some pretty nice construction which generalizes Playbig graphs. And yeah, so that's and parallel with us, there was this work by 6 authors who also found cluster structures in types ADE. But I think we have local acyclicity, and for us, it's important to have local acyclicity because yeah, that's where you get unimodality. And but you can also get QT symmetry and unimodality from this result that Eugen mentioned yesterday, which holds for any knots. So yeah. Right. So if you project this open Richardson to a parabolic flag variety, such as the Grassmannian, well, in some cases it's going to be isomorphic, so you can get any Positroid variety this way. But we haven't thought about actually projecting them in other ways which don't give us Positroid varieties. Yeah, that's a good question. We haven't thought about arbitrary projections to parabolics.
question for Joel Kamnitzer. He asks, do you know any relation between QT Catalan numbers and two-row Springer fibers?
Two-row Springer fibers versus QT Catalan numbers. No, no, I don't. Yeah, I mean there is of course well-known relation between Springer fibers and QT Catalan numbers by counting these different cells in the cell decomposition, but yeah, I don't know what a two-row Springer fiber is. So yeah, I don't know anything beyond what is like well known in this area.
Are there other questions?
There's a question.
Those Slavic answers correspond to something called scannable divides.
Scannable divides.
There are also there's a special class of Slavic graphs which come from whole divides. For them.
Yeah, so the question is, can you prove this result for Playbig graphs which come from divides in this paper by Fomin, Pilavsky, Shust, and Thurston? And the answer is we cannot. I mean, arbitrary divides don't really help us. Like the Playbig graphs are more general than divides, but yeah, we couldn't do this for, yeah, this is basically, has to be leaf recurrent. And for divides, I'm not actually sure if this doesn't come from, yeah, anyways, this doesn't come from a divide. Yeah, but we don't know how to do this.
Are there other questions in the room or in chat? All right, thank you.